Hi guys, we're going to carry on today from where we left off doing numerical methods. So this is further numerical methods. We're going to have a look at the other two methods. You're going to, in the assignment you're asked to use the one we done last week, which is the trapezoidal rule, and the last one we're going to do today, which is Simpson's rule. But cover this mid-ordinate rule for completeness, really, so that you've got all three. With the mid-ordinate rule method of numerical integration, each interval of width d is assumed to be replaced by a rectangle of height equal to the ordinate at the middle point of the interval, as shown in the diagram. So here's an interval. There. So we've still got a width d, but the height of it is the value of that function in the middle of that interval. So hence the mid-ordinate rule. And if we do that over the range that we want between a and b, we've got here the points a and b, so we're going to integrate between the limits a and b. We can say that the mid-ordinate rule says an approximation of the integral between a and b is that it's the width of the interval multiplied by the sum of the mid-ordinates, which looks a less complex formula. However, determining the mid-ordinates is a little bit more time-consuming than the actual ordinates themselves. Only in that you need to find out the value of the midpoints of the intervals. They might be easy, they might be difficult. Okay, but it's best served by us having a look at how we would use it to repeat the example we were doing last week, the function 2 over the square root of x between the limits of 1 and 3. In the notes I've added to this page that the answer using mathematical methods, using integration, was 2.928 to 3 decimal places. Using the trapezoidal method with 4 intervals was 2.945 to 3 decimal places. So we got that there for comparison. So we're going to use here the mid-ordinate rule with 4 intervals first to evaluate 2 over root x dx between 1 and 3. So what are the values of the mid-ordinates? How do we find out what the first mid-ordinate is? We're starting at x is equal to 1. And we're splitting it into 4 ordinates. So we start on here. We must have 1.5, 2, hang on, mid-ordinate values. How do we do it? We're splitting that up into 4, aren't we? So there's 1, 1.5, 2, 2.5, and 3. So the first mid-ordinate must be halfway between 1 and 1.5. Second mid-ordinate is halfway between 1.5 and 2. And the third, 2.25. And the fourth, 2.75. So now we have to evaluate the function y is equal to 2 over root x for each of those ordinates to 4 decimal places, 1 more decimal place than we need in our final answer. Right, what results have we got then? First one. 1.7889. Second one, Jack. We're looking for a final answer to 3. Dom, sorry. And the third one. And the final one. Yeah. Okay. So there are mid-ordinates. So very simply, an approximation of the approximately equal to the width of the interval. It's the width of the interval. Yeah. 0.5, yeah, times all those ordinates added together. Equals. So it equals 2.920 to 3 decimal places. So about 8/1000th away from what we got using the mathematical method. Yep. It's closer than 4 intervals using trapezoidal method. Yeah. So, please have a go at doing the mid-ordinate rule with 8 intervals. Didn't we? In the last problem. And we had 1, and that's 1.5. 1.2, 2.5, 3, and so our mid points were halfway between 1 and 1.5. We're now going to split each of them in 2 again. Yeah. So our width of interval, instead of being 0.5, is now 0.25. So the midpoint is going to be half of 0.25, isn't it, along? So it's going to be 1.125, 1 1/8. Yeah? And your width of your interval is now 0.25, a quarter. Well, an eighth is 0.125. Yeah, because you've got to add 1.125 onto the second ordinate. Yeah? We're not being given any extra data for the mid-ordinates. So all we can do is say that, and that are the ordinates, and these are the mid-interval values. Yeah. Okay, that's all you can do with that. So there's a limiting factor of this, where you've got that data. You need the data more regularly to be able to or at different points really, be able to use this method.
First and last order, is that 1 plus 3?
Hang on. No, the values of the first and last ordinates, yeah.
Right, so then the order
Let me do this one on the board, and then you can do the 8 intervals on your own. I mean, you won't do that, would you? By Simpson's rule, between 3 and 1, 2 over root x dx is approximately equal to 1/3 times the interval width, 0.5, times first and last ordinates, the value of them. So it's 2 plus 1.547 plus 4 times the even ordinates. Let's put that down here. Even ordinates are 1.6330 plus 1.2649 No, it's not. We're talking about the number of the ordinate here. First ordinate, second ordinate, third, fourth, and fifth.
Yeah, but it means there's 2 even ordinates.
Yeah, 2 and 4. That's what I put down. Them two.
Yeah, then the final one.
And then the remaining odd ordinate is this one.
Yeah.
So it's plus 2 times 1.4142. Close the big brackets. Do you get that now or not? This is the position of the ordinate on the x-axis. Yep. This is the value of a function at that value. When it's talking about odd and even, that's talking about the odd and even ordinates. Because it's n ordinates. Yeah.
Sum of even function of an ordinate.
If you say, guys, so that 3.928 to 3 decimal places using 8 ordinates was it Simpson's rule is exactly the same as the answer to 3 decimal places using mathematical integration methods. So on the surface, Simpson's rule is likely to get you the closest to the actual value of the integral. That's on the evidence we got so far. Okay? So if you can use Simpson's rule, maybe you'd clump and say, "I'll always go for Simpson's rule," but you might find that you don't actually need to. You can use one of the easier ones. Okay, there's nothing particularly difficult about it. Just, if you had a lot of data, then maybe that's a spreadsheet problem. Likely to get you closer with a fewer number of intervals than anything else. But you'll do an investigation in the assignment that will allow you to evaluate that in some way. All right? When I'm ready to give it to you, Don. All right? So in summary, I find I got a wrong value on there. Never mind. Put it right now. That's 2.994. Should be. Just summarise all the values. 2.945 we got trapezoidal with 4 intervals. 2.932 with 8 intervals. So it's quite clear that if you add intervals to trapezoidal method, if you can, then you're going to get closer. 4 interval mid-ordinate was 2.920. 8 intervals gave us 2.932. 4 interval Simpson's rule 2.929 and 2.928. Exactly the same as the mathematical method when we used 8 intervals with the Simpson's rule. Okay, so the final thing for you to do today, other than the further problems at the end of the notes that I've given you to have a go at, is to do the river problem using Simpson's rule. You have got, because I've made sure you had an odd number of ordinates, so you can use Simpson's rule on that and see what value you get. So the area is approximately 34 meters squared, therefore flow rate is approximately equal to 2.05. What did we say it was? 69.7? Meters cubed per second. Okay? And we can't say, are you all happy? You all understand that we can't say which one is the most accurate result for the river problem. Not definitely, because you've only got the data that you've got. You've got no mathematical method, but what you can use what you've learnt from doing Simpson's rule with the mathematical function and the other two, to say Simpson's rule more likely to be the closest one with the same number of intervals. Certainly the mid-ordinate, you've had to reduce your number of intervals to go halfway between anyway, so that's likely to be the least accurate. But from what you've done with the other function, you can be pretty confident that Simpson's rule is more likely to be the closest. Yeah? If we go back to the riverbed, if there's a sharp difference somewhere between 2 points like that, you're going to lose that, whichever rule you use. Yeah, that you haven't got data about, because you've only taken it at 1.5 meter intervals across the river. The only way around that, the only way to get closer is to take more intervals, more measurements. All right? Yeah. In your